at our lecture for today. So we've seen, so we started with fundamentals of calculus part 1. We looked at part 2. We went to use substitution. And then when we started this semester, we looked at integration by parts. We looked at trigonometric integrals. And now we're looking at trigonometric substitution. Now, these methods are very, very important, all right? So when it comes to trigonometric substitution, you're going to know that this is a technique you have to use based on how the integral is going to look like. So the first thing you're going to see is if you see something like this in your integral, all right? So if you see a square root, take note there must be a square root. So if you see a square root and some number a, so a squared minus x squared, that is a substitution you're going to use, all right? X equals to a sine of theta. Very important, please, when you make this substitution, you need to tell me that theta lies between minus pi over 2 and pi over 2. Many people tend to leave this thing, all right? Make sure you show me this. And take note, you're going to make use of this kind of trigonometric identities to simplify this root, all right? So when you make this substitution, so we put in this substitution in there, you're going to need this identity for you to be able to simplify your result, all right? Similarly, if you see a root and then you see a squared plus x squared, now there's a plus. The first thing that comes to mind is a tan. So x becomes a tan of theta. Theta lies between minus pi over 2 and pi over 2. You can see I'm not including the endpoint. So these are open bound. So if I have to write it another way, I'm going to say x is an element. I'll do this. All right. I'll use round bracket. All right. Round bracket means use excluding the endpoint. All right. But in the first case, we had something like this square brace to show that we're including the endpoint. And obviously, this is a trigonometry identity you're going to use to simplify the root, everything under this root here. And then finally, you get something like square root x squared minus a squared. This is a tricky one where people tend to forget what is happening here. This one is a sec. So x is equals to a sec theta. Now take note the two intervals here. So theta lies between 0 and pi over 2, or theta can lie between pi and 3 pi over 2. Now, if I give you an indefinite integral, means there's no bound, you need to state these two. If I give you a definite integral, obviously, looking at the bounds, you're going to see which one you're going to choose, all right? So if I give you a definite integral, it can't be both of these. It has to be one of the two, because you can see in the bound where those upper and lower bounds fall. Either it's going to fall in this first interval, or it's going to fall in the second interval, right? But for indefinite, try as much as possible to state these two. Some of you only know how to state one. But if I don't subtract so much mark for not stating these intervals, the most you're going to lose is half a mark, all right? And this is the identity you're going to use. We use the identity sec squared minus 1 is equals to tan squared theta, all right? Now let's look at some examples. Let's look at example 1. So for example 1, just use a different color. First thing you notice is how do you know this is a trigonometric substitution? You see there's a root here. That is the key there. There is a root. If you don't see a root in your integral, it is not trigonometric substitution. It's as easy as that. There must be a root. I see a root, and then I look. Oh, there's a 9 there. The 9, I can write 9 as 3 squared. There we go. It means my a is equals to 3. All right. So my a in this case is just equals to 3. Because the formula says we need a squared minus x squared. So I know that 3 squared is equals to 9. Therefore, it works. All right. Now, what do? I let x to be a sine theta. Remember, a is 3. So x is 3 sine theta. Remember what I told you? You need to tell me that theta lies between minus pi over 2 and pi over 2. Obviously, if you differentiate x, so dx would just be 3 cos theta d theta. Straightforward and easy. Now, everywhere you see x in this root, just put in, or in the whole integral, just put 3 sine theta and then simplify that and see what happens. Let's start with this root. I have root 9 minus x squared. If you put x is 3 sine theta, you end up with square root 9 minus 9 sine squared theta. If you factor out the 9, notice you end up with 1 minus sine squared, which is cos squared. And the square root of a number squared is a number. So in this case, you just have 3 absolute value of cos, which is just 3 cos theta. All right, very important. It's just 3 cos theta. Now, what does the integral become? Take note, the reason why I'm showing all this working on the side, so this whole thing that I'm doing here is so that when I come here in the integral, I'm just going to put 3 cos theta in the place of this whole root here, because I've already simplified that and I've shown the working. You can show it on the side, or you can choose to show it inside the integral, this whole work that we did up here. You can show it in the integral, it's fine, all right? Or you can do it on the side and then you just come and substitute what you have here. This is 3 cos theta. Now, if you do that and you substitute dx, remember dx is 3 cos theta d theta. If you put it in, and at the bottom we had an x squared, so it becomes 3 sine squared theta. If you simplify, look at what you get. You just get cos squared over sine squared. And take note, cos squared over sine squared is cot squared. All right? Cos squared over sine squared is cot squared. And we know there's an identity that says 1 plus cot squared is equals to cosec squared. All right? So I tried to show you how I got the identity up here. And this is another step leading to the identity. But if you forgot your identity, go back from basics. Start with sine squared plus cos squared equals to 1. And then divide all through by sine. Notice that you end up with 1 plus cos squared equals to cosec squared theta. Why am I writing this identity? Because I've seen a cot squared and I don't know how to integrate that. But I know that if I make cot squared the subject in this formula, I'll get cosec squared minus 1. I know what the integral of cosec squared is. I know what the integral of 1 is. Therefore, I'm good to go. All right. So let me scroll down so that we see what happens. All right. So, yes. Someone has a question?
Can I please? No, I don't want to ask a question. Can I please get permission to record the video?
All right. The session is being recorded. So the videos, like I said, it will be made available by the end of this week. I should share it via OneDrive, or probably it's already on Blackboard. For those that are registered, you will see it on Blackboard. For those that are not registered, I'm still making a plan how I'm going to send everything as a whole, or share it via OneDrive or so. All right. But if you can record it from your site, it's fine, as long as it doesn't disrupt our session. I don't have any problem with that.
Yeah, right. It doesn't disrupt the session. It just says I should get permission from you.
Okay, in that case, it means everyone is going to need permission. So for now, just say that just ignore it, because I'm recording already. Like I said, I'm going to share a link to the video.
All right.
All right, let's go back to a session. So 1 plus cot squared is cosec. Remember, if you see something like this cot, please don't think too much. Think of an identity. When you're dealing with trigonometry, you see something that you don't know what to do, think of an identity. It will always work out. I see cos squared, I don't know what to do. I think of the identity 1 plus cot squared is cosec squared. It means that if I make cot squared the subject, I have cosec squared minus 1. And what's the integral of cosec squared? It's minus cot. How do I get that result? We know that the derivative of cot theta is minus cosec squared. It means that if I integrate cosec squared, I should have minus cot theta. And the integral of minus 1 is just minus theta plus c. I've seen many times students, you tend to stop here. I don't know why you stop here. If you look at the original question, it's in terms of x. And you can't give me a result in terms of theta. You think that you're done, all right? You're not done. So you need to go back to x. How do I do that? You go back to your substitution. Remember the substitution you make? Your substitution was x is equal to 3 sine theta, all right? So that was your substitution. So using this substitution, what you're going to do, you're going to draw a right angle triangle. You ask yourself, if this angle here is theta, what is sine of theta? Do you agree sine of theta in this case? So looking at this substitution that you made earlier, if you make sine of theta the subject, you get x over 3. And we know sine of theta is opposite over hypotenuse. There we go. You see, I just put x and I put a 3 there on the hypotenuse. If I solve for the adjacent, I apply Pythagoras theorem. You get square root of 9 minus x squared. All right. And the reason I'm doing that is because look here, I have a cot theta. I should be able to use this triangle to give what the value is. All right. I need to be able to give cot theta in terms of x. So cot theta in this case, remember, cot is 1 over tan, which is equivalent to saying cos over sine. We already know that tan is opposite over adjacent. Therefore, cot is going to be adjacent over opposite. Remember, there's a minus sign there. And then theta, you can make theta the subject directly again from the substitution that you made. Theta will just be arc sine or sine inverse of x over 3. And then very important, say plus c, because it's an indefinite integral. All right, this question usually counts for a lot of marks. If you can get right up to this final point here, then you know already that you've collected a lot of marks. All right. Please practice this kind of questions because definitely you're going to see stuff like this in your test. Make sure you're familiar with this kind of question. Let's look at the next example. All right, example 2 is just to find the area enclosed by the ellipse. All right, so I give you the ellipse. The ellipse is x squared over a squared plus y squared over b squared equals to 1. So go down. All right, so get my pencil again. Now I've given you this ellipse and I'm asking you to find the area enclosed by this ellipse. I know it seems a little different from the way I asked you in example 1. Example 1, you can see the integral, you can see the root, you know already it's a trick substitution. But in this case, like I said, you don't panic, all right? If you see stuff like this, the first thing you want to do is you try and make y the subject. If you make y the subject in this formula that I gave you for an ellipse, you notice that your y becomes plus or minus b over a square root x squared, a squared minus x squared, all right? Why is it plus or minus? Because if you look at this diagram, the plus part represents this top piece here, and the minus part that represents this bottom piece here, all right? There you go. So now how do you approach this question? The first thing you're going to ask yourself is, remember that if you have to sketch this on the XY plane, this point here is just A0, and this point here is 0B. So we can focus on this first quadrant alone, and then we multiply our result by 4. All right, if you can find the area of this first quadrant only, to find the area of the complete ellipse, what do you need to do? You just multiply that result by 4. So the formula says that 1/4 of the total area, which makes sense because this shaded region here is just a quarter of the total ellipse. So 1/4 of the area that we're looking for is just the integral. Remember, it's in terms of x is going to be from 0, which is the origin, all the way to a. All right, remember at this point here, x is a. So from 0 all the way to a, and then you have b over a square root a squared minus x squared dx. All right, by now, most of you should be familiar how you're going to do this, because it looks like example 1, you have a squared minus x squared. That tells you that it's a sign, all right? The substitution is going to be a sign. And how does that work? You let a to be a sine theta, so you let x to be a sine theta. If you differentiate, you have a cos theta. You need to do change of bound, all right? Why? Because I'm moving from x to theta. This is something I need to mention. Whenever you have a definite integral, means you have bounds. There must be at some point in time a change of bounds, all right? If you don't do change of bounds, you most likely going to make a mistake. So we do change of bound. We say when x is 0, so we have 0 there. When x is 0, what is theta? Where do I substitute? I put it here in this substitution that I made here. So if x is 0, theta becomes, so sine theta just becomes 0. Sine inverse of 0 is 0. That's how I got 0 there. Now, when x is a, which is the upper bound, so when x is a, what happens? I put a again in this substitution. What happens? I get a divided by a is 1. Sine inverse of 1 is just pi over 2. Remember, sine of pi over 2 is 1. That's why your theta is now pi over 2. So you now have new bounds. Again, simplify this root on the side. You see this root here. I'm just simplifying on the side just so that I don't make my integral to be messy. All right, I do it on the side. Where I see x, I put a sine theta. I simplify, end up with a cos theta. Now in the integral itself, you see wherever I see the root, I'm just going to put a cos theta, and I'm going to substitute the value for dx. I put my new bounds. And if you integrate and simplify, you apply fundamental theory of calculus part 2. Remember, at this stage, you need to apply fundamental theory of calculus part 2. So you put the upper bound, you substitute the upper bound minus the substitution at the lower bound. You end up with a result that looks like phi AB. Guys, please practice this example. Make sure you're very comfortable. If you don't understand something, send me an email, make an appointment, or see the tutors. All right, you have a WhatsApp group, ask questions in your WhatsApp group. Let's look at example 3. All right, example 3. For example 3, all you need to notice that things have changed a little bit. Now we have x squared plus 4, all right? Remember, in the previous 2 examples, it was the sign substitution because you had a squared minus x squared. In this case, this looks like the x squared plus a squared that we've seen before. So what substitution comes to mind is tan, all right? It is tan. And take note, 4 is 2 squared. It means your a is 2. That's why you see there's a 2 there. Very important, tell me this interval here, theta lies between minus pi over 2 and pi over 2. You see I'm excluding the endpoint. When you do a tan substitution, you exclude the endpoint. Now if you differentiate, you just have 2 sec squared. As usual, I take out the root and I simplify it on the side. So I'm just simplifying the root. Everywhere I see x, I put my 2 tan theta. If I simplify, I end up with 2 sec theta. Now when I go back to the integral, you see where I see the root. All I need to do is to replace it with 2 sec theta, which is this result that we have here. And then obviously there was an x squared here in the beginning. So x squared, I'll just put 2 tan theta squared, which is just 4 tan squared theta. dx, you know what dx is. You got the result from here. That's your dx. And the next you just need to simplify. So cancel like terms. Notice that you end up with sec theta over 4 tan squared theta. Guys, when you hit this step, do not panic, because I know most of you are going to say, what can I do? Is this a U substitution? Is here identity? Please, whenever you have a sec and a tan, go back to the definition of sec and tan in terms of sine and cos. All right, that helps a lot. You see, sec is 1 over cos, and tan is just sine over cos. But because the tan is at the bottom, that's why it becomes cos over sine. Notice it. This cos cancels one of the cos there. And once you see something like this, you know this is just a U substitution. Why? Because if I let U to be sine, which is there at the bottom, the derivative of sine is cos, it appears there at the top, and it's going to cancel out, all right? You know U substitution is going to work. If you do your U substitution, you end up with a quarter du over U squared. If you integrate, you end up with a quarter minus 1 over U plus C. As usual, remember, you have a U. Initially, I asked you, it's in terms of X, but now you have U. So first thing, you need to go back to theta, and then from theta, you need to go back to X. How do I go back to theta? I look at the U substitution that I made. U is sine theta. It means everywhere I see U, I put sine theta. 1 over sine theta is cosec. Again, I don't stop here, all right? Although I've already made the substitution for U, I don't stop there because I'm looking at the original question. It's in terms of X. It means my final answer has to be in terms of X. What do? You resolve to right angle triangle. You go to the substitution that you made here. Very important is this substitution. This trigonometric substitution that you made in the beginning is what you always use in your right angle triangle. So if you put that in there, sine theta is, so you had tan theta is x over 2. Remember, tan is opposite over adjacent. And if you solve for the hypotenuse using Pythagoras theorem, you just have square root x squared plus 4. There you go. If you substitute that, you have your result.